Today we will be starting a new section. We will be focusing on heat transfer analysis or thermal system analysis. In fact, kind of the first non-structural problem that we are tackling using the finite element method. I will only highlight, let's say, the analogies between the structural and non-structural parts and give you the basic equations, and we can directly jump to tackle a heat transfer problem which can be solved using the finite element method. Why the first question that we would like to answer is, why do we need familiarity with the heat transfer problem? In a heat transfer problem, our main aim is to determine the temperature distribution within a certain profile or within a given element or within a given component. Since we are interested in the temperature distribution, we would like to calculate temperature at different parts of the bodies, provided it is subjected to different boundary conditions. For example, assume that a system is subjected to, let's say, a heat flux, and of course there's a heat source embedded inside the element or the component. Then you would like to model the temperature distribution within the component using the finite element method. What you can do is, for certain problems, you will be able to write analytical equations and you will have closed form solutions in certain cases, in certain cases which are quite straightforward or which are standard problems. But when it comes to, let's say, complex geometries or complex objects which contains a lot of components made out of different thermal conductivities and different material properties, then the problem becomes complex, and using the finite method such as finite element method will be quite useful to tackle such problems. So in this section, first, in the first part, let's try to revise our basic heat transfer knowledge before we move on to analyzing a one-dimensional heat transfer problem. Then we will, maybe in the next session, we will be also looking at two-dimensional heat transfer problems. Let's see within this section how what are the important equations and what is really happening when it comes to solving a problem, heat transfer problem or thermal stress problem using the finite element method. Let's first move on to get some familiarity with the one-dimensional heat conduction problem, that is without convection. Let's try to derive the basic differential equations so that we know what we are planning to model using the finite element method. So in this section, we are trying to get an understanding about the physics of, let's say, behind the finite element code. Section 9.1, let's say, derivation of basic differential equation. And specifically, let's look at one-dimensional heat conduction without convection in the first place. So first, let's try to define a control volume in order to get the physical terms into account. Let's consider a control volume having a cubic, let's say, formation, a typical cubic, let's say, volume, which we also consider when we want to write down the mass conservation and energy conservation when deriving, when applying these physical concepts. So let's try to write down the basic differential equations, let's say, for one-dimensional heat conduction problem. So the idea of this derivation is for you to, or for us to get a physical understanding about the process so that we know what we want to really formulate, what we want to develop using the finite element method. Consider this control volume, which has a length of, let's say, dx, and on one surface, say the heat flux into the control volume can be defined as Qx, and heat flux at the exit or the other surface can be defined as Qx plus dx. Now, this x corresponds to, of course, the since we are considering one-dimensional heat conduction problem, so the x-axis directed on this direction. At this surface, at the first surface, call it S1, let's call it S2. Surface 1, the heat flux, we define it at Qx, and the exit or the output heat flux is Qx plus dx. Then let's assume that there's an internal heat source embedded inside the control volume. Let's define it as Q, and the cross-sectional area of this cube can be defined as capital A. Now we simply use conservation of energy. What is conservation of energy means? The input energy should be equal to, let's say, the output energy of the system. We do an energy balance. So when we consider the energy balance, the input energy plus whatever the heat generated inside the control volume should be equal to, let's say, the change of the internal energy, or in this case, the stored energy, plus the whatever the heat output from the system. Simple energy balance. Okay, right. So now we can, since we are already familiar, or we have already defined heat flux terms, we can rewrite these equations using heat fluxes. So what is the input energy? Input energy is nothing but the heat flux at surface 1 multiplied by the area. So the heat flux is defined as, let's say, the energy or the power per unit area. So something like watt per square meter, or kilowatt per square meter, times the area, which will give you the energy per unit time, which has to be multiplied by the corresponding time. Yeah, so we get the total energy. The generated heat is, let's say, Q, which is in watt, of course. Again, since the heat generated by the source, or in this case, it can be also sink also, but it is defined with the units, let's say, power per unit volume. Yeah, heat generated per unit volume. So in this case, you have to multiply by the control volume, that is square cross-section area times the thickness of the control volume gives the total volume. The whole term has to be multiplied by the corresponding time that we like to perform the analysis, which will give the energy. Let's deal with the corresponding delta U part separately. Whatever the output at the exit or at surface 2 is written by Qx plus dx, heat flux at the exit, multiplied by the cross-sectional area multiplied by the time. Quite straightforward. If we think about the units, or of course the energy entering inside the system is given by, let's say, either using joules, or you can also define it as kilowatt per hour, or if you use imperial units, it's given by BTU. Delta U is the change of stored energy, again can be written using either of these, let's say, terms or units. The heat flux, of course, as a flux, always we define a flux as, let's say, the heat power per unit area. Similarly, Qx plus dx also has the same units, and T, of course, is the time which we can define in seconds, hours, or yeah, basically in seconds or hours, depending on which type of whether you use the SI units or whether you use the imperial units. Right. So since we consider this to be a one-dimensional heat transfer problem, of course, there will be only heat transfer taking place in the x direction. The other surfaces are, let's say, for the moment, consider them to be insulated. Okay, so we know the Q is the, let's say, internal energy source or internal heat source, which is given by, let's say, with the units heat generated per unit time per unit volume, which is positive because it generates heat. But if it is a heat sink, of course, where the heat is drawn inside, let's say, drawn out of the volume, then the Q, overall Q value, should be negative. Of course, the cross-sectional area, which we consider in this problem, which is A, is perpendicular to the direction of the heat flow, that is perpendicular to Q. We can apply the simple, of course, Fourier's heat conduction law to write down the relationship between, let's say, the temperature gradients and the heat flux. So we would like to obtain an expression for heat flux. What does the Fourier's law of heat conduction tell us? That the heat flux is proportional to the temperature gradient, and the proportionality constant is given by the thermal conductivity. Yeah. So the negative sign we include because it is opposite in the direction of the heat transfer takes place in the opposite direction of the temperature gradient, or in the opposite direction of the temperature increase. That is the intention of including a minus sign. Here Kxx refers to thermal conductivity in the x direction, and we know the temperature is given using either Celsius degrees or Fahrenheit. So Kxx defines the thermal conductivity, of course, in the x direction, and dt divided by dx. Okay, here T defines the temperature in Celsius degrees or Fahrenheit degrees. Of course, also in Kelvin degrees, you can define it. Okay, T divided by dx refers to the temperature gradient. It is quite clear that you can find, let's see, find an analogy between this heat transfer, let's say, and let's say momentum transfer and mass transfer problems. Yeah, depending on which type of problem you are tackling, the constitutive equation, the physical equation will change. Because in case of, let's say, if it is a momentum transfer problem, yeah, the stress, the shear stress is proportional to the velocity gradient, and the proportionality constant is the shear viscosity. And similarly, if it is, of course, a mass transfer problem, the mass flux is proportional to the concentration gradient, and the proportionality constant is called the Fick diffusion coefficient. And even furthermore, we can think of an analogy from what we have already learned from, let's say, one-dimensional stress strain problems. If we think of stresses and strains, the stresses in the x direction, we said that it is stresses can be written in terms of the modulus of elasticity times the strain. The strain could be written as du times dx, and of course, even so, in this case, you can see the constitutive equation which we have already used is sigma x equals that is stresses in the x direction is modulus of elasticity times the velocity or the strain in the system. So similarly, we have already used the thermal conductivity to relate the heat flux to the temperature gradient. Nothing new, only the physical quantities varies. So let's consider, so we have written the heat flux for the first surface. If we consider the x surface, the other surface 2, similarly, we can write down the heat flux at x plus x dx is equal to the temperature gradient evaluated at x plus dx multiplied by the proportionality constant, thermal conductivity minus sign because the heat flow occurs in the opposite direction of the temperature increase. So since we are at this point now, what we can do is we can rewrite this equation. So let's try to obtain an expression for this heat flux at x plus dx using the heat flux at the surface 1, that is using qx. So let's try to express the heat flux qx plus dx using qx terms. For that, we try to recall, let's say, the Taylor series expansion. In the general form of a Taylor series expansion can be written as, if there's a function which can be evaluated at, let's say, x plus dx, can be written using the function evaluated at x plus the derivatives also. That is, the first derivative, you differentiate it the function with respect to x and multiplied with the dx, and the second term would correspond to the second derivative of this function with respect to x and multiplied by dx squared by divided by 2. So on and so forth. There can be n number of terms depending on how you would like to discretize the function using the f function, of course, evaluated at x. So there will be different contributions, and the more number of contributions you use, the more accurate the results will be. So in this case, for simplicity and for, let's say, general enough approximation or accuracy, in order to get a decent accuracy, let's consider the first two terms of the Taylor series expansion and write down a relation for qx plus dx. Yeah. So following this Taylor series expansion, let's write down an equation for qx plus dx, yeah, which is nothing but, let's take the minus sign out. We know this minus kxx dx dt divided by dx. Let's take the minus sign out. According to the Taylor series expansion, first we have fx. What is fx? The corresponding function is K, the thermal conductivity times the temperature gradient evaluated at x. Then comes the second term. It is nothing but the derivative with respect to x, derivative of f with respect to x, that is derivative with respect to s. And what is the function of interest? Kxx times dt divided by dx is the original function of the interest. This has to be multiplied by dx. Okay, now we have a term for heat flux at the exit point, qx plus dx, using qx, or let's say the thermal conductivity and the temperature gradient, using this form. Now, mind you, what is the intention now? We are trying to solve this equation. Yeah, this is the equation of interest. So we have defined, let's say, this term using the qx values or using the Taylor series expansion. And now next we are interested in writing down an equation, let's say an expression for expressing the stored energy or the change of the stored energy. How can we write the state of stored energy? It's quite simple. The state of the change of the stored energy can be written as the specific heat capacity multiplied, let's write it like this, specific heat of the material multiplied by with the mass, multiplied by the mass, and of course the change in the temperature. Specific heat is given by, let's say, let's introduce the term C. The mass can be written as the density of the system times the volume. Volume can be written as the cross-sectional area times the dx. So this gives the volume. Rho times the volume gives the mass. So this term corresponds to the total mass. And the change of temperature can be written using dt. So we have a term, or we have an expression for the change of internal or state of the stored energy. C is the specific heat, which can be written in terms of, if we think of the units, it can be kilowatt. So energy, kilowatt hour per kilogram per rise of Celsius degree, or per unit degree. So rho is of course the mass density, not the molar density, which is written as kilogram per cubic meter. Or depending on if you are using imperial units, you can use other terms also, other units also. We can now use, let's say, equations, equation 9.13, 9.15, 9.16, and substitute back into our original equation, that is to equation 9.12, and by rearranging the terms, or by dividing it, let's say using by dividing it by the volume and dt, we can write down a simple, let's say, one-dimensional heat conduction equation. we can substitute all this equation into our original equation, which is 9.12, and then by dividing it after substitution, you can divide it by the cross-sectional area, or let's say A times dx, the volume, times dt, and by rearranging, the one-dimensional heat conduction equation can be written as, which can be obtained. You can try it on your own. You will be able to obtain this equation, which is nothing but the partial derivative of, let's say, the heat flux, so to say, the heat source, rho c times delta T by T delta T. So if we consider, now this is a, let's say, transient one-dimensional heat conduction equation without convection. For if we assume a steady state heat conduction problem, the differentiation with respect to time will be 0. Then the equation 9.17 will become, let's say, since it is a 1D problem, and if we consider it to be a one steady state problem, so the transients become 0, and the partial derivative will be changed into the derivative dx kxx dt divided by dx, have a heat source, and the right hand side terms delta T by delta capital T by delta simple t will become 0 because there's no transient flows considered in this system. So if we consider the heat thermal conductivity of the material is to be constant for the steady state one-dimensional heat conduction problem, we can write down 9.1.8 in this form. Since it's a constant, the thermal conductivity, we can take it outside. The second derivative of T by X plus Q would be able to equal to 0. If we assume, let's say, one-dimensional heat conduction problem, now it's all about applying proper boundary conditions. We can think of a, let's say, slab, let's say infinitely long slab. The heat conduction takes place in the x direction. We can set boundary conditions at the two surfaces, surface 1 and surface 2. We can set the temperature at surface 1. Let's assume the temperature to be, let's say, TB, and whatever the boundary conditions at the surface 2 can be a flux. In this case, of course, let's define it at Qx. If it is positive, we consider the flux to be entering the system. If it is negative, the flux to be leaving the system. And in certain cases, of course, you can find some surfaces to be insulated. In such cases, the flux, the corresponding flux at the insulated surface is 0. And on the other side, of course, you can provide any boundary conditions in the form of temperature. On top of this, you can apply, let's say, certain boundary conditions in order to solve this differential equation. What are the boundary conditions? Let's say, if you think in terms of equation 9.1.9, the boundary conditions, the temperature is equal to TB at surface 1. We assume that the TB is known. It's a known boundary conditions at the surface. The corresponding, let's say, flux entering inside the system at surface 2 can be written as minus kxx dt by dx, of course, which is, let's say, a constant value on surface 2. So we know the heat flux if the temperature gradient is known. And we know in the case, if we have an insulated boundary conditions, we know the heat flux is 0 at that particular boundary condition. So using this, applying these proper boundary conditions, we can solve this differential equation. This is the case for one-dimensional heat conduction problem, that is without the convection term. So similarly, We can also think of, let's say, 2D heat conduction problem without convection. It's quite similar to this expression. If we think two-dimensional heat conduction without convection, a steady state heat conduction problem, we can show that the same equation can be also extended to 2 dimensions. I will not go through the derivations but simply write down the equation which you would get once you perform the derivation. It is nothing but an extension in the dimension. So heat conduction in the x direction. Now we have to consider the heat conduction also in the y direction. Let's assume that thermal conductivity is the directionality are different. Let's say we have a different thermal conductivity in y direction, so you can introduce a new term, delta T by delta y, that is temperature gradient in the y direction. Whatever the heat generated or heat rejected in the system is equal to 0, because we consider the transient to be 0, that is steady state condition. If we consider the boundary conditions, that is the temperature at certain, so maybe it's good if we can draw a schematic for you to visualize what we have done here. Control volume, heat conduction takes place in 2 dimensions, in the x direction and the y direction. So if we apply boundary conditions for a particular surface, we can consider temperature equal to be Tb, which is a known quantity. Let's say at surface 1, let's say we can define a surface depending on how you like to define, of course. And on another surface, because here we define a temperature on a particular surface, on the other surface we define a heat flux. The heat flux on another surface, let's say, can be written in this way with the help of directional cosines. I will let you know as to what we mean by this. This is a constant at surface 2. What do we mean by directional cosines here? If we think of, let's say, a surface, let's say if we think of a surface, an additional surface, and if we assume the heat flux goes to be perpendicular to a given surface, to an arbitrary surface, let's consider this surface to be S2, right? And the heat flux into the system, we call it, let's define it as plus Qn, yeah. So this surface is now inclined, and the unit vector, which is normal to the surface, is given by n, which is having a theta degree to the x direction, and 90 minus theta degree, of course, to the y direction. So you can translate this Qn term both in the x direction and y direction. If you want to write it, the effective flux on the S2, you can write it in terms of, let's say, with the help of directional cosines. You simply take the corresponding contributions. So there should be a C, another term here, C by term, to multiply with this term. So directional cosines for the 2 fluxes acting in the x direction as well as y direction. The total flux can be written acting on the S2 surfaces, can be written in this way. Yeah, this is something that comes, of course, there are that we have to apply. There are surfaces which are oriented in the xy plane in a different angle. If you want to translate the, we want to calculate the total flux when we consider 2-dimensional heat conduction problems. Next, before we move on to, let's say, dive into this finite element topic again, or the method, it's quite easy if we can quickly work out, let's say, address the heat transfer problem, including the convection, so that it will be easy for us to, let's say, derive, let's say, 1-dimensional heat transfer problem for the using the finite element method. So what if we consider now, let's consider the heat transfer problem with convection. Why do we need to consider a solid which is in contact with a free flowing fluid at the solid to fluid interface? There is heat transfer taking place in the form of convection. It can be a forced convection or a free convection. If an external pumping or external force is used to draft away or used to um, uh, input, let's say, to include used to induce a flow, then it's a forced convection. And if no external forces or flows are present, then the convection takes place due to natural, of course, buoyancy forces, due to temperature differences, local temperature differences. We call it then natural convection or free convection. So let's try to also include this effect of convection also into this heat transfer problem. We can consider a control volume in one dimensional, which includes heat conduction and also convection. As in the previous case, let's consider a control volume, a cubic control volume. And so it's a cube, actually. Then we can define the fluxes. It's in the previous case, input to the system as well as fluxes out of the system. And there's an internal heat source. Let's write it as Q. Let's assume that the temperature outside is, let's say, T